Welcome to winter. I'm uh, glad to be back in class with everybody. I hope the job fair went reasonably well. Did people go? Was it moderately productive? Good. All right. My feeling is like we're turning the corner, but I'd be interested to hear from you about it. Today we're going to talk about transactions and some of the concepts that are around transactions. I'm also using a new layout. Hopefully this is big enough for you. You're all young, so I hope that the smaller font is okay. But this helps me see what the next slide is, so it's not quite as bumbling when I'm going through things. So I hope that's okay. But earlier in the course, I did mention very briefly the notion of transactions, particularly when we were talking about JDBC. And what I want to do today is really show you how the JDBC API works with transactions, demonstrate it in action, and then also discuss some concepts around transactions. Earlier on, when we were talking about JDBC, I mentioned how the connection by default is in what's called auto commit mode. And what that means is that every SQL interaction that you have with the database is sort of its own thing, and it either succeeds or it fails. And that turns out to often not be the behavior that you want in the real world. You often want a series of operations to either succeed or fail as a unit. Early on, I mentioned the ACID properties of the database. And so what we're going to do today is go through them in more detail. So ACID stands for atomicity, consistency, isolation, and durability. And transactions are the primary tool that are used in databases to ensure some of these things. So what is atomicity? Well, you guys probably know, if you're computer science students anyways, you know that atomicity is an operation or a set of operations either entirely complete or entirely fail. They're atomic. The idea is if a database goes down halfway through this insert, you wouldn't end up with sort of 4 of these values inserted into the database and the other values not inserted into the database. This insert statement is going to be atomic. Okay, it either succeeds or it fails. There's no halfway. If you've ever written a file to disk before, that is not an atomic operation. So if the power goes out halfway through a loop where you're writing a bunch of data to a file, then the file just has half the data, and that's all there is to it. And so it requires more sophisticated techniques in order to ensure that, yes, the data has been written to disk. Atomicity doesn't only apply to one statement, it can also apply to multiple statements. So here's an example where we're moving 10 bytes from the track with track ID 1 to the track with track ID 2. Why would we be moving bytes between tracks? I don't know. It's an example from the schema we're already using, so sue me. But in some world, we want to be able to move bytes between tracks. And here we have an update of track 1 to basically subtract 10 bytes from it. And here we have an update to track 2 to add 10 bytes to it. And what happens if track 1 goes down if the database goes down after this first operation? What happens? Yeah, you've effectively lost 10 bytes in the overall system, right? Like 10 bytes have been removed from track 1, but they have not been successfully added to track 2. Now, this is a silly example, but what if this were bank accounts, which I think I mentioned earlier when we were talking about transactions, rather than tracks? This could be a serious issue. And when you transfer money from your account from your savings account to your checking account, for example, then you want this, even if the power goes out, you want to make sure you don't lose money. Okay? So consistency is, a database will have consistency constraints placed on it. And one of the consistency constraints placed on the tracks table is that the number of bytes in the tracks is constant over time. And so by failing to make these 2 operations atomic, we're violating the consistency rules that are in place for these particular tables. Another aspect of ACID is independent or independence. Hey guys, I'm sorry, do you mind? Is that cool? Yeah, it's all good. Independence, if we have two users that are working with a database at the same time, and they both run this operation, then they both need to effectively work independently of one another. They need to be independent of one another. And that's actually more subtle than it seems at first. It doesn't just mean only one person is allowed to modify the tracks table at once, because here we have a dependency between these two operations, right? And so this update is going to read the number of bytes for track one and then write it, right? It's going to read it and write it. And if two people are accessing that row at the same time, what if the following series of operations happen? What if user 2 reads the number of bytes, then user 1 reads the number of bytes and writes the number of bytes of track 1, and then user 2 writes the number of bytes in track 1? You see that interleaving of operations that could happen there? And what would happen in that case? The update would be reverted back. So rather than decrementing by 20 bytes, which is what should happen, we would only decrement by 10 bytes. And it's because of the interleaving of the reads and the writes in those two users that are hitting it. And if you took 366 with me, we talked about this same problem. And what did we use to solve it? If you took 366, don't worry if you didn't take 366, but locks. We use locks to prevent this sort of thing from happening. That's what's called a dirty read. The user 2 would have read data that became dirty when user 1 updated it underneath them. That's what that's called, as a dirty read, okay? So it's a classic computer science problem, and here it is in the real world when we're trying to move bytes or money or whatever it is, whatever operation, higher level operation we're trying to do, these things do come up in the real world, okay? Durability, so this is the last, this is the D in ACID, guarantees that if the system crashes, after it has told a user, yes, you're good, committed, then when the system restarts, the state of the system is going to be such that it is as if that transaction occurred, okay? So what that means is when a database tells you, yes, I have committed this data to the database, even if the power goes out after that, it's not going to be a situation where you restart the database and that even though maybe consistency and other things have been taken care of, that transaction has not been committed. Okay. This is typically implemented with a technology called a transaction log, which we're going to talk about on Friday. We'll go a little bit into the details about how databases achieve this, because again, as you know, with files, when you're working with a file and you're writing data out to a file, you have no guarantee if the power goes out that the data that you're writing gets to disk or not. It could die anywhere between, the instruction writing that piece of data out to disk and the actual physical disk itself. So how do you achieve this guarantee in a world like that? And the answer is transaction logs, okay? So, those are the ACID properties of databases. And I think I mentioned earlier, one of the things that became hot when I was younger were NoSQL databases, which relaxed the ACID constraints in the name of speed, typically. The problem with ACID is that it's really expensive. So we went through probably about a decade of people kind of saying, oh, this is all, databases are for fuddy-duddies, you should use MongoDB or something like that instead. And the industry, I think, has by and large backed off of that and has come to appreciate the value that these ACID guarantees give to us. And so transactions from a practical standpoint are how we work with the database to guarantee that the consistency constraints that we want placed on interactions between different SQL expressions as well as different users are satisfied, okay? And you do need to, and we'll see this here in a little bit when we talk about isolation levels, you do kind of need to pick what level of ACID you want. That sounds kind of bad, but you do need to pick the level of consistency that you want, because there is a trade-off against performance, in databases. And SQLite's kind of an interesting case. We'll talk about that in a second. So logically, a transaction is a collection of database. It's a property of transaction, or excuse me, of statements interacting with a database that have to be executed atomically. And either everything needs to succeed or everything needs to fail. And in SQL, the syntax for starting a transaction is begin transaction or start transaction. Depends on the database. To be honest, unless you're writing raw SQL yourself, which is pretty rare in the industry these days, you're typically not interacting with the database like this. You're not issuing begin or start transaction statements. Instead, you're using an API like JDBC to start transactions and so forth. You can use commit to commit a transaction. So here we begin a transaction, we make these two transfers, and then we commit. And until this commit statement succeeds, there are no guarantees that this is going to go to the database. So if the power goes out anywhere between here and here, it will not be in the database. The database will not reflect these changes. However, if we get to this point and the power goes out and it says, yes, you've committed, if we turn the database back on, we will see the results of of those statements, okay? You can also use rollback to roll back a transaction. That can be useful if you get to a point with a series of SQL statements and then you decide, no, I didn't want to do that, and so you want to roll the whole thing back. You can issue a rollback. And again, in JDBC, there are APIs for this, so I'm going to show you that. Again, I'm going to keep reiterating this. In JDBC, connections are by default auto commit, and this can get you into trouble if you don't understand what the transaction semantics are of your system. So you need, as developers, when you go out into the real world and you start working with databases in whatever language it is, Python, Java, PHP, Go, whatever it is, what are the transaction semantics? Like, I want to make sure I'm not accidentally auto-committing data that should be part of a transaction here. You need to understand that. And I'm going to be honest with you, there's probably a non-trivial percentage of you that's going to go into companies or universities or government work or whatever, and they're going to be like, what's a transaction context? Like, what does that mean? Okay? You're going to run into environments where people just don't understand this. And to be honest, to be honest or to be frank, it often doesn't matter until it does. But to me, I think that's an important thing for you as software developers to understand. I need to understand what the transaction model is for the software if I'm going to write data safe software, okay? So in JDBC, everything starts in auto commit mode, and it is, that is what it is. I've got a little demo here that I want to show you. So this is, I'm going to update artist 1 to foo and artist 2 to bar, update their names to just something stupid to change their names to something obvious that we can see in a database. And what I want to do is I'm going to run this test. And right now I've got a connection from a database. This is just using the driver manager to get a connection directly to a test database. So I update artists and set name to foo, or artist ID is 1. That's AC/DC. I think 2 is Aerosmith. I don't remember. But in between these two statements, I call do something. What does do something do? Well, it throws an exception. So not very good code, but it'll demonstrate what's going on. So if I run this test, it's going to fail. I'm going to get an error. Oops, cool. And if I open up the database and I go take a look at it, I'm going to have to refresh this database. And I look at artists. We're in a situation where artist 1, I guess artist 2 is accept. I don't know what that means, but whatever. But the name of the artist 1 is set to foo, and the name of artist 2 is not set to anything. And why not? Because an exception occurred right here, right? If you've never seen this before, you can click on the stack trace and see exactly where things happened. So right here, an exception occurred that this first statement was committed to the database because this connection is in auto commit mode. And the second one obviously never executed. right? It never executed, okay? So if I wanted this to be transactional, rather than, or if I wanted the whole thing to be atomic rather than non-atomic like it currently is, individual transactions, what I need to do is on the connection, mark it as auto commit equals false. And then when everything is done, when I'm ready for, I've made all the modifications that I want as one atomic unit, then I can say connection.commit, and that will actually commit it, okay? And so now if I rerun this test, make this a little bigger, and if I rerun this test, there's still going to be an error, but if I come here and refresh the database and reopen the artist table, I gotta close that, sorry. Come here, refresh, and open the artist table. You can see AC/DC is still the name of the first artist. So even though I had made it past that statement.execute, because it was part of a transaction, it was not auto-committed, it waits until it sees a successful commit to write all of that data to the database. And so if I go back here and I comment this out, so I'm no longer spuriously throwing an exception, and I run this, the test will pass now because no exception is thrown. And if I come to, and I got to close everything up, well, let's come here, refresh, artists. You can see that foo and bar are both set in those first two artists because I made it all the way through. I made it to that commit. And so that's the database, that's the JDBC API sitting on top of database transactions, allowing me to bind two database operations together by setting auto commit to false and by committing when I'm satisfied, when I'm ready for everything to go to the database. Question?
Will the JDBC tell you if there have been failed transactions, or is that something you need to log?
What's that?
Will it tell you if it's encountered a failure, or is that something you'll need to?
What do you mean a failure?
Like it didn't complete the full transaction.
Yeah, so if you're connected to a database and something bad happens, like the database crashes or whatever, it'll throw a SQL exception, and you'll typically see something like that. As far as it reporting, like, and by the way, I rolled back transactions, it won't tell you anything about that. It'll just say the database like disappeared or whatever. You'll get some network socket related thing, but it doesn't tell you. Now we could, instead of committing here, we could roll back instead, okay? And if I do this and I run this with a rollback and I refresh my test database and I open up artists again, oops, I gotta close this, open it again. You can see that even though those two statements succeeded, no exception occurred. Because I decided to roll back, they didn't hit the database. The transaction was rolled back. And so this is how you work with transactions in Java. And so you might roll it back because you get to some point, you check a folder and something isn't in the folder. Oh, I just need to roll the whole thing back, roll the whole transaction back. This is the way that you would do it, okay? So that demonstrates how transactions work from Java. Question? Could you pass parameters and set the rollback? You could certainly pass in a flag and check at various points in a complicated series of statements. You could also, you know, a not uncommon situation is to catch an exception and to roll back at that point and then rethrow the exception. I've seen that pattern a lot too. So you can really do whatever you want with the transactions. The important thing to understand is, first of all, normally there's no multi-statement transaction in Java. Check whatever programming language you're working in. And then almost every programming language that you work with is going to have some sort of API like this, where you can start a transaction. Here, starting a transaction really means set auto commit to false. And that'll just start a single transaction at that point. And then commit or roll back, depending on, you know, what happens, okay? That's the general API or the high level API you're gonna work with in other systems. okay? So that's what it looks like in Java. Now there's more to transactions than just starting them and committing them or rolling them back. There's also something, there's a concept associated with transactions known as isolation levels. And what isolation levels are a way to say sort of how intense the transaction is in ensuring that data consistency is preserved. So they effectively allow you to pick what level of consistency am I concerned with. And with isolation levels, you're always trading off against performance. Okay, you're always trading off against performance. Isolation levels effectively boil down to locking. So again, harkening back to 366, when we talked about locking a single piece of data. Well, in a database, you've got a bunch of data. So it gets very complicated. Like you've got locks for all sorts of data. There's really sort of two axes on which you can split this up. First of all, do you lock on operations or not? And the two operations for a database are reading and writing. So given a piece of data into the database, you can read that piece of data or you can write that piece of data. And the data that can be locked on are typically rows and tables. So you can lock a table, you can lock a row. I've never seen it where you lock a cell, like a particular column in a particular row. It's always been row locks and table locks that I've been familiar with in my working career. But who knows, there's probably something that's crazier than that, okay? So there's a series of isolation levels. From your perspective, this is good quiz material, but in the real world, we're going to talk about optimistic concurrency on Wednesday. You're probably going to have your isolation levels determined for you, but it may come up in specialized situations, particularly around performance work, where you need to talk competently about these things. So you're not going to need this for, any homeworks or whatever. There might be one quiz question on it. Just get the high level concepts. Remember the term isolation level and performance when you're out in the real world. So serializable is the most restrictive isolation level. And what serializable means is that all reads and writes are locked. So if you read a piece of data, that piece of data is locked, which means no one else can read it. No one else can write it. Okay? No one else can read or write it. And that's very serious. Like you own that data at that point, and no one else gets to look at it until you're done. In addition to that, any ranges that are satisfied by a where clause are also locked. Now that might sound weird. It prevents something called a phantom read. And let me see if I can explain it. Again, I'm going to use a somewhat silly query to do so, just because it's from our schema, okay? So update, this should be update, not updates. Update track set name equal to a dash, and then this is concatenate in SQL. Remember it means concatenate in SQL name. Where ID in, select track ID from tracks where name like a %. What is this query saying? It's a silly query. But it's a good example. Yes. Yeah, add a hyphen to the front of every track's name who starts with an A. Why would you do this? You wouldn't. It's a good example for this particular situation, okay? So when I say that the range of the where clause has to be locked, what that means is that for this case, there's a where clause. What's the range of this where clause? What's that? It would be all tracks, right? Because it's asserting something about every single track. Either it starts with an A or it doesn't start with an A. What's that? Right. All tracks are part of this where clause because they either satisfy it or they don't satisfy it. And so at the serializable level, you would have to lock the table, the entire table, because you don't want another person adding a row that does start with an A or updating a row that has an A so that it doesn't have an A while you're proceeding. Okay? You don't want anyone else modifying any data that could affect the where clause. And this where clause involves the entire tracks table. So to make this query serializable, we've got to lock the entire table, okay? And so what would be an example of a phantom read? Well, if someone, while we were issuing this transaction, inserted a new result, or updated an existing row so that it started with an A. After this query had started, when your query had finished, it would not see that row if we allowed them to make that update. And that's what's called a phantom read in database terms. There was a read that should have happened that didn't. So you're going to look at the data and be like, how come this row starts with an A, but it doesn't have an A hyphen in front? And the answer is because it wasn't in serializable mode, and someone inserted that data during the query. Okay, all about the concurrent modification of data. All right, so that's what a phantom read is. Okay. Next isolation level is what's called repeatable reads. And on repeatable reads, all reads and writes are locked, but you don't do range locking. So you wouldn't lock the table. You would accept, all right, if I'm issuing this query, and someone inserts a row at the same time with an A in it, I'm going to be okay with not catching that. And that might be okay, it might not be okay. It depends on what you're doing exactly. Depends on what you're doing exactly. Okay. This is a less expensive way of serializing your data it's a less expensive isolation level than serializable is. Okay. Question.
When you say expensive, is that like actual money or is that like efficiency?
So the question is that expensive money or expensive efficiency? And the answer is both. I mean, they're pretty much the same thing. The throughput that you're able to achieve with serializable transactions is much lower. And so you're not able to get things through as quickly as you are with something like repeatable reads. Let's see here. No risk, yeah. You're not, so I guess like the takeaway here, or the crux with repeatable reads, is the situation that you're not going to have is you've read a row that has an A in it, and then someone modifies that row. Okay, you could have someone insert a row underneath you because you're not locking the whole table, but you are locking every row that you read. So repeatable reads means if you read that data again, you're guaranteed it will be a repeatable read. You'll be able to see the same data from that row again. So you're locking the rows that you've read, but you're not locking the whole table, the whole range. That's what makes it less expensive. Okay. Next level up is read committed. And in read committed, you lock writes to the database. But reads are only guaranteed to be part of a committed transaction. So they're not guaranteed to be repeatable. And so if you set your isolation level in a transaction to read committed and you issue a query like this, then someone can mutate rows underneath you that are part of this, the positive results of this query, until you update them. Once you've updated the row, other people can't update it underneath you. Because when you update it, it's going to write lock that row. Okay? But in that in-between phase, when you're reading from the row, there's still an opportunity for someone to modify it, as long as that modification is part of some other transaction. So that's what read committed means. Okay. Read uncommitted is the least expensive thing you can do, and basically writes are locked reads can be part of an uncommitted transaction. So what that means is that when you're reading a piece of data, you're not even guaranteed that that data is going to be there when you commit, even if nothing else touches it, because you may be reading data from a transaction that is going to be rolled back later. Okay? It's the least expensive because it does almost no locking, almost no read locking, only write locking effectively. Okay? So that's very fast because all you have to do is write lock the things you're going to modify, which I hope makes sense. Like you're always going to have to lock things you're going to modify, but you don't concern yourself with any other sort of locking. Okay? So this is the fastest isolation level available for transactions. So if you want to set the transaction isolation level in SQL, it's set. It depends on the database, but it looks something like set transaction isolation level serializable or set transaction isolation level read committed. By and large, this is not a decision that you, the developer, are making. This is a decision that's been made by the tool that you're using to work with the database. We're going to talk about ORMs starting next week, and that's almost certainly how you're going to be working with a database in most cases, and it's going to have its default isolation level, and you're just going to use that. It also gets bound up in something called optimistic concurrency, which we'll talk about on Wednesday, okay? But you can do this, and in JDBC, you can connection.set, is it isolation level? Set transaction isolation, and you can pass in constants to set what you want the isolation level to be for that connection. So it is doable, but it's complicated. So it's not something that a junior developer should probably be doing. It's something that someone, you know, who has a lot of experience with the data architecture, knows the database, knows the data access patterns and so forth is deciding. So hopefully you don't have to decide it. If you do, send me an email and I'll do my best to help you. But it's just hard, okay? This is pretty complicated stuff. But back of your mind, isolation levels, important for data consistency, important for performance. Like, remember that concept in the back of your mind. Okay. SQLite, it turns out, runs everything as serializable. And I said serializable is what? Good or bad for performance? Bad. It's really bad for performance. So why are we using a database that uses that by default? Well, it turns out that SQLite is kind of, again, a special case as far as databases go. Because it's a local database, it runs on the same machine as the system that's accessing it, that it's so fast that it almost doesn't matter. And a lot of like rules that we're going to talk about from a performance standpoint for quote unquote normal databases actually don't apply to SQLite. So even though SQLite uses serializable as its default transaction level, it's so fast that it almost doesn't matter, which is kind of bizarre, but that's just the way it is. I don't know what to tell you, okay? It's at the same time, SQLite is not good for high write output applications. If you are writing a ton of data, then SQLite is probably not the right database, particularly if you're trying to aggregate that data from multiple sources. So other databases do much better for high transaction throughput than SQLite does. But if you are mostly reads, if you're doing mostly reads and occasional updates, then SQLite can be very good. And most websites are mostly reads. You typically aren't updating all the time on websites. You're typically mostly reading. And so SQLite has become more popular for websites because of that, because it's so fast for reading, okay? If you want to issue a particular strategy, so the way the databases work around these things is not magic. There's no magic under the covers. I told you in 366, how do we deal with concurrency? It's got to be locks. So what does that mean exist in databases? Locks. Lots and lots of locks. okay? They've got to have locks for tables and for rows in particular. And so those are going to be data structures that live in database software, just like when you write software, you've got hash tables and, array lists and all the rest of it. It's the same thing. It's more complicated, obviously, but it's fundamentally the same conceptual ideas as we talked about in 366. So serializable has to acquire read locks on all data that are everything that's read, everything that's written, obviously, and then any ranges that are selected over during a query. Those locks have to be acquired. Now, read locks are when you read a piece of data, okay? And typically in databases, multiple threads can acquire read locks for the same piece of data because it's not dangerous for two people to read the same piece of data. Just all the read lock guarantees is no one's going to update it underneath us. That's what the read lock guarantees, okay? Write locks, on the other hand, can only be held by one thread, by one thing at a time, okay? So only one thread can be updating a piece of data. And more generically, if one thread has a read lock on a piece of data, another thread can't acquire a write lock on it, because then they could modify that data and violate that read lock, okay? So we have two threads that are contending for a piece of data, one reading and one writing. If the read lock is acquired first, the write lock will not be able to be acquired, okay? When we have locking, and we talked a little bit about this in 366, there's some issues that come up. The first one is what's called lock contention. So what is lock contention? It's when multiple threads are trying to acquire the same lock. So how could that happen? How could that happen? Well, if you have, for example, a request count single row in your database that you use to keep track of the number of requests in your system, and every time anyone makes a request, you update that one row, what does that mean? That means every request has to lock that one row. So that is a highly contended row of data in a database. And that's a great way to bring a website to its knees, by contending for one piece of data. And so that's why it's typically not a good idea to use a database for things like aggregate statistics like that. You would use something like an atomic int or something like that in Java, or Redis, which we'll talk about later, for something like that. But if you have lots of threads that are working with a database, say through JDBC, and they're all trying to update the same pieces of data, there's almost no way to make that perform well, because there will be lock contention almost no matter what you do, okay? Lock and contention can also occur if you choose too high of an isolation level. So if you decide, all right, everything's going to be serializable because we're writing a banking app or whatever it is, cool, but if you have queries that have where clauses that have a broad range that they apply to, you're going to be locking tables. And if you're locking tables, that can easily cause contention. So obviously, if you're trying to update one row in one table, that's going to cause contention. But if you're using something like serializable, then you're basically making the whole table its own atomic thing. And so a bunch of threads will be fighting over that lock. So it's not just one piece of data that we're contending over. It's also what's my isolation level, and what is the lock contention that it implies. And this is why, again, most databases do not use serializable, even though that makes the strongest data guarantees. That's why they would not use it, because of the performance implications of it, okay? Another issue with locks is what's known as blocking. So this comes up when someone acquires a lock in a long-running process. So someone starts a transaction in a batch server and then starts inserting data in some batch process. And that batch process takes half an hour, and then they commit. the database is going to sit there locking rows and tables quite happily as long as that thing's going on for half an hour. And if your website needs some of those rows in order to render a web page because of your isolation level or whatever, then you're going to be waiting for a long time. Your users are not going to be able to see any web pages. They're not going to be able to get any results out of the database to render to a web page anytime soon. So that's what's known as that's blocking. That's when you've got long-running processes. And so long-running processes are often built specifically to not lock rows for long periods of time. They might window their inserts, for example, something like that, and they'll end up sacrificing some consistency or some atomicity in order to make things perform better, because you don't want to hold locks for a long time. It's one high-level thing to take away from this lecture. Don't hold locks for a long time, okay? Another issue, and this again, we talked about this in 366, is what's called deadlock. So deadlock occurs when you have two different threads and they each hold a lock that the other thread needs. So thread 1 or transaction 1, same thing, holds a lock on student and needs a lock on grade. Transaction 2 holds the lock on grade and needs a lock on student. That's deadlock, because transaction 1 cannot make progress because it needs a lock transaction 2 has. Transaction 2 cannot make progress because it needs a lock that transaction 1 holds. See how those two locks are deadlocked with one another? It's like, if you've ever been in a situation where two people are trying to turn left and the traffic is backing up behind them so they can't do it, that's deadlock. It's the same thing here. Neither of these transactions can make progress. Most databases today actually have pretty sophisticated deadlock detection. It used to be, if something like this happened, it hung your system and it would just hang there and you're like, oh, I'll restart the database server. Looks like we got a deadlock somewhere. Now databases have gotten pretty smart about detecting this situation, and they'll terminate one transaction and throw an exception saying deadlock detected. And it'll give you a pretty good idea of why of the locks that were causing that. So today in the professional databases, especially like the Oracles and the SQL servers and so forth, they worked hard to make this a better situation for us. When I was first starting out, though, it was very common to accidentally lock up your database because of things like this. Okay? Okay, so that's transactions. Transactions are the big takeaway here. Transactions are how we ensure consistency in database and how we achieve the attributes of the ACID guarantees that databases give to us. But we have to do it. It's not automatic. We as developers have to take advantage of the tools that are given to us. And a big part of that, or a significant part of that, is the isolation level that your transactions are running at. Isolation level is a complicated topic related to performance and consistency and that trade-off that you have to make. Typically not something a junior should be doing. If you're asked to do it as a junior, reach out for help because it's a complicated topic. You have to get things right. You have to understand the whole data architecture in order to make these trade-offs effectively, okay? Transactions use locks under the covers for these things, just like we talked about in 366. There's no magic. Yes, it's complicated software, but they're using locks just like we use locks in 366. And just like in 366, the problems that come up with locks are contention, blocking on locks for a long time, and then worst of all, deadlocks. Deadlocks are really the worst case scenario with locks, okay? So that's transactions. Again, in JDBC, you're going to want to set auto commit to false and then explicitly commit or roll back a series of operations. This is the code that you're going to need. You'll need this code for the next homework. This is what the code in homework 4 looks like, okay? This is the API that Java presents to you for working with transactions. You can set isolation levels, but it's probably a bad thing if you're being asked to do that, okay? Okay, I'll see you guys on Wednesday and we'll talk about